That's nice. That's nice to meet
CEO,
all.
exam in charge are there. All the participants, faculty members from our department. We welcome everyone for this online FDP scheduled by Department of Electronics and Telecommunication.
Thank you. It's nice meeting all of you, though virtually.
Thank you for sparing your valuable time, sir.
Yeah, it's my pleasure.
Sir, we'll start in a couple of minutes.
Oh, yeah. No. Please take it. Yeah, I'm there. I'm ready. Maybe I can kind of just check once if the slides are okay.
Yes, please, sir.
Can you see my slides?
Yes, sir. Yes, sir.
Okay, I'm trying to go full screen. Let me check.
Perfectly fine, sir. Perfectly fine, sir.
Now I'm moving the slides. Can you see the moving of slides?
Yes, sir.
Oh,
Yes, sir.
okay, sir. Okay.
Principal sir, we are ready. Should we start the session?
Yes, sir. Please go ahead. Start.
Yeah. Ankur sir, you can go ahead now.
Yeah.
Please start the
Thank you, sir.
recording.
A very good morning to everyone present. Myself, Professor Ankur Ganurkar from Electronics and Telecommunication Department, MCT's Rajiv Gandhi Institute of Technology. Good morning and welcome to all the dignitaries present, our chief guest, Honorable Principal Sir, HODs, all the faculties present and the student. Department of Electronics and Telecommunication Engineering, MCT's Rajiv Gandhi, proudly presents to you Industry 4.0, the way forward, an online FDP program for 3 days. We will like to inaugurate the event with a Saraswati Vandana. I request the technical team to play the Saraswati Vandana. Thank you. And I again wish good morning to everyone. Now I would like to request our Honorable Vice Principal and Head of the Electronics and Telecommunication Department, MCT's Rajiv Gandhi Institute of Technology, Dr. Sanjay Deshmukh sir, to brief us about the FDP event.
Thank you, Ankur sir. Very good morning to one and all. Respected dignitaries on this virtual dais, respected chief guest for inaugural function, and eminent speaker for today's session, Dr. Satyanarayana sir, who is Senior Scientific Officer at Tata Institute of Fundamental Research, Mumbai. Respected Principal of our institute, Professor Dr. Sanjay Bokade sir, heads of the departments, associate heads of all the departments, CEOs, TPOs, teaching and non-teaching staff of our institute, organizing team, and dear participants. It is my pleasure to welcome you all for this inaugural function of 3 days faculty development program on Industry 4.0, the way forward. which is organized by Department of Electronics and Telecommunication Engineering of our institute, MCT's Rajiv Gandhi Institute of Technology, Mumbai. Electronics and Telecommunication Engineering Department of Majra Charitable Trust, Rajiv Gandhi Institute of Technology, Mumbai. It was established in the year 1992, and it caters undergraduate program of in electronics and telecommunication with intake of 120, a PG program in masters in engineering in EXTC, which was established in the year 2012 with the intake of 18, and the department also has a research program leading to PhD degree in the area of electronics and telecommunication engineering. The Department of Electronics and Telecommunication Engineering meets the requirements of technical manpower requirements as well as technological challenges through its qualified and experienced faculty members, skilled supporting staff, and well-equipped labs. The academic excellence is also reflected in more than 95% results in the final year. Our alumni are working in responsible positions in many multinational companies. The department has an exceptional placement record with most of our graduates. They are making to leading core as well as IT sectors. The department has a good record of organizing seminars, workshops, symposium in emerging technological areas for the overall development of the student as well as faculties. Dear students, dear participants, we see rapid developments happening in the industry today. Various industry experts have mentioned already that the market is moving rapidly towards industry 4.0, due to which there will be significant change in the technology. So it's very high time that our faculties as well as students learn the skills which are needed for the industry and as per the requirements of industry 4.0. The objective of this FDP is to create awareness about various ideas or approaches that are deployed in industry 4.0 and its various components such as data science, cyber security, blockchain, and so on. We are very fortunate that we have speakers for this FDP who are very eminent and are at key positions in the respective fields. It will be a great opportunity for all of us to attend and learn from their experiences. On behalf of the Institute and the department, I would like to offer my sincere thanks to eminent speakers, Dr. Satyanarayana sir, who is a scientific officer at Tata Institute of Fundamental Research, Mumbai, Mr. Sagar Gajra, who is the manager of Cyber Practice, Mumbai, Dr. Sunil Karamchandani, who is a professor at DG Sanghvi College of Engineering, and Madam Nikita Katyal, who is a senior data scientist. On behalf of the department, I thank everyone for accepting the invitation for the function and enlightening us on various ideas and approaches that are used in Industry 4.0. I express my sincere thanks to all the participants for their overwhelming response. We have received participants from various parts of Maharashtra. Thank you for your support. We are extremely thankful to our management for giving us the opportunity to organize the FDP and extending continuous support. On behalf of the department and on my personal behalf, I would like to extend my sincere thanks to our respected principal, Dr. Sanjay Bokade sir, for his valuable guidelines, support, and help. We really appreciate it, sir. We acknowledge the support received from heads of the department, faculty, and staff members. Thank you, everyone. And I thank all for joining the online session today for this FDP. I hope it will be a great learning experience for all of us. Thank you, everyone. Over to you, Professor Ankur, sir.
Thank you, sir. Now I would like to invite our Honorable Principal, sir, MCT's Rajiv Gandhi Institute of Technology, Dr. Sanjay Bokade, sir, to enlighten us with few words.
Yeah, thank you. Dr. Satyanarayana, sir, the eminent speaker for today's function, Vice Principal Dr. Sanjay Deshmukh, all the heads of department who are present for this function, all the attendees of today's function, participants, students, very good morning to one and all present here. I was extremely happy when I came to know that the Department of EXTC is going to take up the program on Industry 4.0 as a way forward. And I believe that this is the most needed thing which should be frequently spoken, so that the teaching faculty gets updated with the new upcoming technologies of Industry 4.0, so that they can align their teaching in a way in that the current industry demands for. Here, of course, about Industry 4.0 and various enabling technologies and the various contents within it would be, we would like to hear it from Satyanarayana, sir. But being the fraternity of teaching, I feel that we have to look at this whole thing also with one additional dimension. And the dimension is we are trying to understand what is Industry 4.0, what are its technologies. At the same time, we have to see that how we can map our education with the Industry 4.0's demand. We have some rigid curriculum. We have certain rigidity in the curriculum because something is told to us, prescribed to us by our authorities, and we have to teach. But there exists always a gap between industry and your curriculum. So it becomes our awesome responsibility that we identify this gap and we bridge this gap also. So as Industry 4.0 has got certain revolutions, the first one when manufacturing started with the help of mechanism, the second one, the revolution was when it was mass production concept. The third one was when it was all automation going on, and this one it is all it is integration of all the technologies. We also have to look how our education system has grown up step by step, has got revolutionized within itself step by step, and how we could see when there will be when there is the era of 4.0. We need to see that how we can facilitate our teaching, or rather teacher should be more of facilitator. We should be in a position to deliver the content where the possibility of remote learning shall be as much as possible. There should be personalized
नोटबुक
attention to
पेन
one
पेंसिल
student,
सगळं घेऊन बस
and we also should look for various opportunities like of teaching, like we go for some project based teaching. And in this new system of education, data should be on the tip of your fingers. One who is getting graduated or learning onto something, the data is, and that is actually possible because technology has brought a day where industry is now going to take its new revolution, because everything comes when the facilities are developed first. So many different things are, and this is one good opportunity for the teachers of technology institutions, that new learning is now available for them. They can learn this new learning and discharge that learning to our students. So I wish all the participants to have some good session, some good takeaway from this session. And I close my talk here. Thank you so much to all of you.
Thank you very much, sir. Now I would like to welcome our guest speaker for the day, Dr. B. Satyanarayana, Scientific Officer, Tata Institute of Fundamental Research. I would like to give an introduction for the sir. Dr. B. Satyanarayana has done his BTech in Electronics and Telecommunication Engineering from JNT University, Hyderabad, and PhD in Physics from IIT Mumbai. He is working in the Department of High Energy Physics, TIFR, since 1983, and currently a scientific officer head and a coordinator of IONO project. He has published more than 250 research paper proceedings in the national and international conferences and journal. His very first paper has won the Best Paper Award by Institution of Electronics and Telecommunication Engineering, IETE. Recently, he was honored with Homi Bhabha Award in Scientific Education HBASE 2020 and has been selected as AICTE INAE Distinguished Visiting Professor at Symbiosis Institute of Technology, Pune. Dr. Satyanarayana is a fellow of Institution of Electronics and Telecommunication Engineer IETE as well as Institute of Engineers IE. He served on many of the doctoral and expert committees as well as academic council, boards of studies and advisory boards on college, universities and many national organizations. Dr. B. Satyanarayana is senior member of IEEE. He is currently the chair of IEEE Bombay section. He previously served as Vice Chair Secretary, Chair of Technical and Professional Activity Committee of the section, as well as Chair of its Signal Processing Society. He served as an Executive Committee member as well as a Vice Chair, Technical Activities of IEEE India Council. He won IEEE Bombay Section Outstanding Volunteer Award for 2014 and IEEE Headquarters MGA Achievement Award for 2016 year. So I welcome sir and I request you for a keynote and initialize the session for the day.
Yeah, thank you, Professor Ankur. Am I audible?
Yes, sir. Thank you, sir.
Okay. Thank you for your kind words. And I must first thank my old friend Piyush Dave for the invitation.
Thank you, sir.
Dr. Sanjay Bokhadi, the principal, Dr. Sanjay Deshmukh, the HOD, the Expertise department, and also the vice principal, all the heads of the departments and all the faculty members of RGIT, and then the participating faculty and students. It's often said that the best way to learn is to teach. In fact, we all learn much better than what we knew yesterday by teaching to someone, talking to someone, articulating to someone, explaining to someone, and so on. This is something which you do every day in your institute. And then, every time you teach to, even if you teach the same subject semester after semester, but you'll actually teach to new, different set of end beneficiaries, different set of students, and different combination of students coming from rural to urban, girls, boys, and so on and so forth, and coming from different and social and economical and whatever backgrounds. Why I say this classification is because everyone brings with him or her something new understanding about what they see the world before they enter the steps of your college. And those questions often open up something quite new, which we didn't know the previous semester. And we end up actually, brushing ourselves up or maybe learning something, reading something and so on. This is what I meant by saying, when you teach, you actually learn, and teaching is never a one-directional activity. But when the situation that we talked about typically in the educational institutions, academic institutions, we must admit that there is always that thin line that remains between the academic knowledge, obviously on which you are experts, no doubt on that, but also the industrial applications or the applications of these concepts once the student gets out of the college. So in order to kind of bridge this gap, needless to say, we must agree that we must continuously try to update and upgrade ourselves to bridge this very thin but very important gap. I say this because these days more and more the employers, like the industries, often now demand from the students, and also I'm sure from you, that it's not that the student, how much the student is academically bright, and how he or she scored in various subjects, but we would like to have them so-called industry friendly. So this is the word I keep hearing every time I interact with academic institutions. What they really meant is they don't want to spend more time in orienting the student towards their daily duty, which is, of course, depends whether the student joins communication, joins VLSI, student joins some other area of engineering or mechanical, civil, even other branches as well. I think it is in that respect, the faculty development programs like this will really go a long way in delivering this particular value. And I do see, this is very heartening to actually see that more and more such FTPs these days are being held. And I think that is very positive thing. I'll also say a couple of things why it is, apart from, again, unidirectional kind of something you hear from typically industry or research or other faculties and so on, but they also offer very good opportunity besides learning from each other. Some of these novel methods of teaching. Now, you might say that I'm already a teacher, I'm already a professor, and what do I need to learn in teaching? And, as the principal sir very aptly said, facilitating the learning process is something which is a new paradigm in the education technology areas. Okay, and in this new normal that unfortunately caused by this unprecedented situation that we are going through, it again becomes more important to invent newer methods of dissemination, newer methods of reaching out to students. Remember, unlike you have all your students in your classroom in presence, when the students join you from various parts of the town or city, or maybe in rural areas, they do come up with problems, like maybe not so good network, not so good computer at home, and maybe there's not even enough room in the house where they can actually participate peacefully and focus on your teaching. So I know obviously it is causing it's a big hardship, not only to you to suddenly cope up with this new form of teaching, but also to your students. So I know for sure this has been causing, actually it is adding a completely new dimension to already the kind of dimensions that we talked about, namely, how do you kind of adopt and upgrade yourself? Since we talked about this situation that we are going through, I want to kind of say a couple of words on the role of science and technology for human health and welfare, which are the main buzzwords that you hear, has not been so visible and sought after any time before, at least not during our lives, than during the past year or so, due to this particular situation through which whole world is going through. While, of course, many existing technologies could be quickly adopted to deliver new applications for fighting this virus, for example, some novel technologies have already emerged and deployed on absolutely phenomenal time scales. What I meant is, when there is a virus, when there is a problem, and the whole world is suffering, you see human suffering, loss of lives, and I don't have to say this to you. You actually see every day on all the social media channels. So what is important is that even though some existing technologies, you know what I mean. Many of the industries probably producing certain products elsewhere, but they really coped up, they really brought up, upgraded, or went into doing something else, which will address or which will produce something useful to this situation, even though they're actually main line of products or something else. But besides that, there are also completely new technologies which were somehow not there during the pre-COVID, but I mean, they really picked up the need and necessity to kind of course, the business and making money definitely will come side by. But what is important is to rise to the occasion and then, bring up even sometimes technologies which are on the design beds, design tables to bring up and deliver products. And in this respect, some of these technologies that I'm talking about is computerized tomography, which you keep hearing these days almost on daily basis, and a lot of new sensors, especially the low power sensors for digital pathology, which I probably will touch upon a little bit. Robotics, IoT, which is the theme of this conference. And you remember when you talk about, kind of automatically kind of, quantify the images that were of, taken of a patient rather than the human radiologist going through this, are the techniques where now they're used so many of, the AI, ML or DL based image processing systems, image classification systems. They were able to kind of very successfully replace expert radiologists in patient monitoring. See, now, of course, AI, ML has been there for decades. This is nothing new. But what is important is here is a problem. Here is a kind of, suddenly you see instead of 100 patients in a hospital, you see 1,000 patients in a hospital. Now, you can't have, instead of 100 doctors, 1,000 doctors, but that means you really require the technology to bridge the gap between the human expert, and the patient. So, but this has really kind of done a phenomenal kind of progress on it. And much of this healthcare system, of course, in the process has gone digital to elevate some of the real strain that I mentioned to you just now imposed by this coronavirus. Okay, things like what you will hear, telemedicine, remote diagnostics, etc. They're helping patients to get medical advice and diagnosis at home. And imagine, coronavirus has not spared small villages and hamlets, not necessarily in big towns like Mumbai. So you don't have a medical system at par with what is required about these emergencies. When you talk about a village, you talk about certain patients. Yes, that's true. And most of the time, the patients do. The people there in village, they don't really rush to the nearest town. Most of the time, they just do some kind of self remedies. But corona was not like that. It has actually swarmed like a wave of. Incidentally, they're all called waves, right? Now, therefore, you can't redeploy a large amount of experts or medical teams in small towns. So that's what I meant by saying the telemedicine, remote diagnostics have actually come to the rescue. It's not actually uncommon from the history, what I told you about. That rapid progress of science and technology areas were not just made during the periods of peace and so on, but quite often you will find that they're actually made during human suffering. I mean, this is really bizarre in some way to say, but so many of these technologies, we'll talk about it a little bit later, that came up today or were actually invented during world wars and during pandemics and so on. So, as I said, it may actually sound a little bizarre, but this is also, I think, unusual opportunity for especially the students. I'm sure some of you are there on the call to latch onto this, to work on these technologies and produce products and applications for the society. Now, when I say this, I didn't really mean that a student who will start today will be able to produce a product which will get deployed tomorrow in a hospital and so on. But what I'm actually telling is that there are always a set of problems to work on for the students. There are always a set of technologies to get familiar with because they are actually wanted by the industry outside. But what I'm actually trying to motivate is here you suddenly come across on your table when you had 10 technologies to work earlier, you had 100 technologies now to latch on, because these have been in some sense forced upon by the situation. But one, as I said, one could also take them as kind of unusual opportunity, right? So I think this is something which the students, especially the senior students towards their third year, fourth year, etc., will find a lot more interesting, a lot more, I would say, intimidating in some sense, because the pace at which these technologies are coming up, let alone the student, even the faculty, it becomes sometimes difficult to kind of cope up and also able to advise very efficiently to the students. So in this context, it's really heartening to know that MCT's Rajiv Gandhi Institute of Technology, the Department of Electronics and Telecommunication Engineering, is organizing this online student and faculty development program for 3 days, I understand. And so I'm really glad to know that many of these sessions I just went through the program are very relevant to the situation that I just described above. So before I conclude anyway, since I'm kind of going to get into again talking to you for a while, I wish to congratulate the organizers and the program a grand success. And I also hope that you will have a very nice learning experience. And as I said, the experience is always both ways. So I'm sure I will too today take something back after I kind of talk to you and interact with you. Thank you very much for this opportunity.
Thank you, sir. Thank you very much for enlightening us with the entire background. Now I would request you to initiate the session for the day.
Okay, thanks once again. I think I'll just try to go kind of seamlessly into my talk. So I'm trying to share my screen. I hope you can see my screen.
Yes, sir.
Yeah, okay. So in the context of the FTP on the IoT, the Industry 4.0, I kind of chose to talk just one small, actually rather couple of topics, which also happen to be something which I work on, though on a somewhat different domain and different application areas. But I guess there is enough commonality about these sensors and signal processing techniques, which we all know they are the key enablers for any IoT system. IoT system always starts with the sensor. Now, the question is, what type of sensor that you are handling and how you are connecting, how you are signal processing, how you are communicating the data. And once that is done, which is more like a hardware domain, and then the entire system of data analytics and getting up the actions out of that, etc., come in picture. So I thought I will share some of my thoughts on it, and maybe there may not be enough time to kind of give my own direct application areas as such, but I mean, that's fine. We can always take up when it is required during the question answer. So let me go, and this is what I just said a while ago. I mean, when do we really look towards technologies and technology developments? You'll be surprised that most of the time we don't care. We know we have wealth, we have power, we have a decent living and so on, and we don't really care what is medicine, what is CT, what is a particular medicine needed for coronavirus or whatever, right? Because things do happen very well when things are happening every day nicely. We don't really look up towards science and technology quite often from the point of humans. I'm not saying from the point of view of a business. But, some old days, if you look at, there are days when most of the things obviously are done manually, and you would like to, for example, improve the production of goods. And when I say production of goods, I didn't actually show an industry, but actually showed an agricultural field. and kind of trying to say that, these are kind of many agriculture activities which are typically done from hundreds of years rather on, manual. And you can really see people doing everything manual. But when you want to take them up into mechanization and rather automation, and then improve the efficiencies and the quality control, the principles, and you want to invent new instruments to maintain the quality control and etc. So this is a very, I would say, a kind of a process that must happen very linearly with the people progress. I mean, it can be starting from saying that, look, I mean, when I'm doing manually, I'm not able to ensure that the lines are parallel, or I'm putting enough exact number of samplings in each one, and a fatigue of humans and so on and so forth. I can't work for 12 hours continuously bending forward. I mean, you can say any of those things. So then the question comes, can I do a certain mechanization or automation? By that I will improve the efficiency and quality control. And this is something strange that I told you just a while ago. You will be really surprised, right? So much of technology that we kind of use today, and they actually have their birth during World War I, World War II. And this is strange, but wars and conflicts between countries or regions is something where you want to do on a competitive scale, on a competitive time scales, on a competitive technology scale. You want to have one-upmanship compared to the other country. Now, so there is a certain amount of urgency, there is a certain amount of strategy, secrecy, and so on and so forth. But the point is that these technologies or these one-upmanship, what I said, are actually driven by the ultimately basic science and engineering research. And since I told you about the World War, I must actually give some specific example. When all this microwave technology, all this electronics technology, all this cryptography that we use today, and many of those, and you will be surprised to find that the entire simulations, entire mathematical modeling, the first computer, and all this have been done by the world's best institutes in US during 1940s. And then instead of doing basic science and the way we said, they were able to kind of quickly turn that into an application, and unfortunately, I would say, used to build bombs and make bombs and so on and so forth. I mean, anyway, those are the results of that were not so good. Of course, we can debate and discuss, but what I'm actually trying to say is that wars and conflicts have become a motivation sometimes to bring up completely new technologies, new science research. And I keep saying again, the world wars are one such example. But the third one, which is more contextual in that sense, is when the entire world, not between two countries, not between two continents, when the entire world actually gets into the human health problems, the diseases and pandemics like what we are going through, it's not between country A and B, it's the worldwide concern in some way. And therefore, it's not like country A is developing something against country B, but country A and B together and in a collaborative way want to kind of elevate the human suffering, and in some sense they work in collaborations. And this is the situation that I just now talked about. And now in this field, it could be science, it could be medicine, it could be pharma, it could be engineering, technology, whatever it is, of all the countries, people are trying to pool and see how we can get benefit out of these. And of course, at the end, one is not talking so much of making money and whatever, but what is important is to see, when we were absolutely hopeless about a year back, when in trying to understand what this new, horrible disease is, and also, how do we elevate it? And in a year from last year, we were able to kind of produce not just the hospital, not just medical technology, but actually the discovery of drugs and production. And today we are talking about all this vaccination. So you can see normally technology developments of that scale doesn't happen in 4 or 5 months. I never see a medicine that is developed with a normal course of, let us say, disease. You never expect it to be delivered in 6 months, right? It never happened in the history of human mankind. But this is what I meant by saying that sometimes we look for technologies into those kind of areas. Now, sir again mentioned, so I will not try to kind of give about the time scale, but going by what we kind of said in the beginning of how things you want to improve on a linear scale, you go back to the so-called first industrial revolution, and as we already mentioned about sort of transition to a new manufacturing process rather than from a very manual kind of jobs, 18th, 19th century, early centuries. Three major industries, if I can point out, is during that time which really blossomed is the textile industry, the iron making industry, but the main power, the energy that is kind of required to do all these jobs instead of manual jobs happened to be steam power. Okay, so because this was kind of one of the the earliest possible adaptation. For example, stationary steam engines, etc., becoming industrially getting used and so on. Okay, and the substitution of coke or charcoal or the fuel cost of iron, etc. Now, these are a kind of inventions that happened because someone wanted to really do mechanized, let us say, cotton spinning powered by steam engines, not by manually somebody doing this chakra, etc. These are issues. These are things which have kind of got into human mind, saying that we want to improve efficiency, we want to improve speed, we want to improve the quality, and so on and so forth. And that, of course, led to, as I said, things like simple machines. Now, again, as sir said, so once you kind of latched onto a kind of paradigm of mechanization, now the question comes: is the steam is the only energy source? These are the industries only that can be done? Of course not, because then people learn from what they did before, right? But there is a scale difference here. Okay, what is the scale difference here? The thing is, first it was coal and steam and what we mentioned here, right? Okay, now by the time we came to the mid 1800s and early 1900s, we already have parallelly looked at petrol and electricity, etc. So your source has become cleaner, your source has become source of energy, much different. Okay, but the main difference is in the first industrial revolution, if you look at it, most of these technology developments had very little scientific base, if I can kind of call that. For example, it did create a chemical industry, but I don't think there is no chemical industry per se, chemical technology per se. But surprisingly, you didn't find a full-fledged research in chemistry. For example, iron industry was there, as we saw, but I don't think there was a science topic as metallurgy or power machinery without thermodynamics. For example, thermodynamics, of course, is all that what matters, right, for these industries. So it's very interesting that the applications of that has come, but without necessarily going into the science behind it and so on and so forth. So this is the big change from the first and second, though both of them you can really see. We are talking about automation, we are talking about mass production in the assembly line, whether you produce aircrafts, whether you produce cars, whether you produce something else, right? So there is a marked difference between these two. By the time we came to the third industrial revolution, of course, we already brought the computer in, the internet in, the renewable energies. Remember, we talked from steam to going to petrol and electricity, and now we go up to renewable energies like solar, wind, and the social realization that, look, not only social, of course, economical also, that we can't really depend on the conventional energy sources like petrol, etc., which will go over after some time. And that has made a completely new gear into the system, and now systems have become such a way that you sit in computer and you produce them. As the figure kind of tend to represent. But what is again another gear, if you want to talk about, this is again automation. We are always talking about automation. But what is the big step in this? The big step is the globalization, the outsourcing, the multinational companies, etc. Gone are those days where you have a company in your backyard, you produce certain goods, you go and sell in your country or in your region sometimes, and then that's all the industry is. But now you can sit in one country and you have the units in other country and producing products for the fourth country and things like that. And then you don't know how to do certain things, and you outsource into some other industry, some other country, and the products are sold into world. So that is the USP. That is the new thing for the third industrial revolution. And topic of today, this is now once again a big change. What now? You don't treat the, I would say, the key enablers as just machines which produce automation, which computers and this power engines and this and no. I mean, now why not you kind of go and try to blur the lines between actual physical and digital and biological spheres. What I really meant is man and machine, right? So this is completely again brought up, linking together completely new services, and then therefore people really found that the apart from the front runners of the technology, something like media, something like communication, something like understanding the needs of the customers, etc. That has actually led to a big way. And digital world as proper has actually changed the entire landscape here. Why it is so important? Because for me, earlier, until let us say third industrial revolution, it actually happened that, okay, I design a product, I sell it, and I kind of try to maybe kind of understand what are the needs, and then I'll go ahead and change my product. But this particular thing resonates more deeply than, as the fourth industrial revolution completely created a kind of landscape where completely distinctive digital capabilities must for both either short term or long term, because without the digital connect between the customers, my own customers, it turned out that I can't really bank on just one product, whether the customers changes, whether the customer needs are changing. And that is again led to something more what is in cooking as of now, and say, the so-called cobots, where you literally work with the robotic, robots or humans or whatever. Now the lines are kind of blurring, and then you want to kind of incorporate those advancements in the workplace and the collaboration that happens between the humans and machine. Now, this big word, again, one more USP for fifth, just like we saw on the fourth, is the so-called hyper-personalization. What it really means is now people want every product personalized to really individual. Now, when you talk about somebody is making umbrellas, you make umbrellas of various designs or whatever, right? I mean, you don't say, I personally want something else. Now, that personalization, which is actually brought to the industry through various digital channels, now you incorporate in your manufacturing a lot of personalized products, which means there will be better satisfaction of the people saying that, look, I wanted in this particular way, I could actually kind of design or part of the specs myself. It's not that products are decided by people. You'll actually see a nice examples of this all the way going into digital electronics a little later, because this is a EXTC department organizing. I will give some example from the digital circuits, but this is the hyper personalization is the key for the fifth industrial revolution. Okay, so therefore it will provide a completely personalized products and services, and obviously the customer is very happy because I want to get what I require to get. For example, there are people who are the so-called righties and lefties. If I'm a lefty, I would like to have a product which is more personalized for me. I don't want to use a product which is optimized for a right-handers because I find inconvenient, right? For example, so that has actually brought a next scale into industrial revolution. So of course, that there has been a lot of new positions and opportunities, and this worry always there. Every time there is an automation, are we actually going to lose my jobs? But that's not. It is actually the human touch which is actually aimed to bridge the gap between robotics or highly skilled. Now, when you get your work done by robotics in a lower level of the jobs, the higher skilled jobs are actually getting available, right? So this is how things have been kind of happening, right? So in this context, when you go from first to the fifth, as I kind of narrated briefly, of course, I didn't go into discussion, but one thing that has kind of emerged in the fourth, where we are trying to connect up things, is the IoT. Where can I mean, imagine a situation where if my idea is to kind of have the data at the center of all these industrial products or inventions, how do I kind of improvise the model of collecting the data, looking at the data, processing the data, and then analyzing the data and making something out of it so that I can plow back into this. This entire circle, if you kind of look at it, there is roughly an upper half and a lower half. I mean, these are actually six segments that one is talking about, starting all the way saying that, look, I mean, if I want to look at a process that happens, or if you want to look at a situation where I need to monitor certain things and so on, of course, I need to have those sensors which are actually picking up the physical quantities, physical environment there in the system. So I would like to go and start about maybe designing, developing, discovering certain sensors, what we all know about it, and embed certain basic intelligence so that they don't have to transfer all the data into the upper part, kind of choking up the communication line, and can they work a little bit autonomously by themselves, right? So those are the devices. The sensor development has kind of not just remained with an electrical engineer, but actually touched upon the material scientists and science in general to find out newer devices, newer technologies, and so on. Right after that, you need to kind of, the signals that are picked up, you need to kind of process them in some way, capture the data in some way, and so on and so forth. Why? Because when you pick up the data from sensor, typically we will see that the data is the signal strength is pretty small, and you would like to very efficiently kind of sense the data and process the data. The most important thing comes at the end, as I mentioned before, is the communication. Because if you have sensors which are spread in, let us say, hundreds of acres of an agricultural field, or maybe a seismological application, how do you collect this data fast enough and efficient enough? Because it's not like I have connected one wire from my computer to some device and transferring data. I mean, these distance scales are quite different. So the communication technology, thanks to, again, parallel developments that are happening in communication technologies today, of course, we talk about 5G and even beyond. So communication technology, the signal processing technology, the sensor technology actually occupy main strategic places in any IoT system. Of course, thereafter, you have very efficient tools. I mean, today we talk about AI and cognitive learning systems, which pick up this data and able to kind of extract out of what you kind of require, and then go ahead and say that, okay, this is why what my data analytics gave me, and these are the ones that I kind of got what you call actionable intelligence. What should I do? What should I do based on the data that I acquired and analyzed? And this is obviously of a great value. Why? Because this is now from the basic information that I picked up and analyzed, I gave value to this data. Now this value, the data is not just zeros and ones, but actually the ones that are going to make a big difference to the humans. And ultimately, right? Ultimately, what one is talking about is how do you kind of benefit humanity? Today we talked about all this pandemic situation and etc. Because ultimately, in the process, you will, of course, every one of us will make money. But what is important is at the end, the benefit actually goes to the human being. Okay. So in this context, we know, of course, what a sensor is. You kind of try to look at a certain environmental parameter, and you want to use a specific piece of transducer, a sensor, whatever, and that is going to kind of pick up some characteristics of the environment in which we are, the sensor is placed. I mean, if you talk about a simple temperature sensor, maybe that's something. But if you talk about want to monitor the patient's certain parameters, maybe an MRI machine, I would like to monitor what is the magnetic field. Maybe I will use some magnetic sensors and so on. And the second one I told you, since the sensor signals are invariably very tiny, and I would like to kind of get a most efficient way of signal process them and always, perform something so that the data can be kind of extracted and moved very efficiently. So these are, of course, some electronic circuits. We can call them as signal processing circuits. As we said in the previous circle, you remember the ultimate actionable items is something which comes from the data. So more often you kind of have so-called actuators, which are actually responsible to kind of see the output from a system, to often go and correct what you would like to do based on your system design. So these are the three main components today when we talk about in this scenario of IoT. But remember, quite often it's very interesting to know, which we'll kind of have some time to talk later, is whether they're sensors, whether they're, let us say, a signal processing circuits or actuator. Very often you'll find all of them are produced using, let us say, a semiconductor technology. So there is a huge opportunity where you can do a technology integration. You could have the sensor, the electronics, and the actuator sitting together using the same technology. So there are specific examples of specific advantages of doing this, right? So I don't want to really spend too much time on actually going and enumerating each of the sensors per se, but I don't have to really tell you that how, starting from very conventional sensors like temperature, humidity, etc., to the sensors that are used in avionics, used in rocketry, and so on, based on the vibration or force or torque and so on. As I told you, the measurements for agriculture applications, and of course, many times even in industry, the piezo films, which play a big role in the accelerometers and dynamic switches, etc. Fluid property has changed the way we look at transport industry and also many of the process industries that we are talking about. And now even not just, there you will actually later you will also see that detecting the speed of an object has become, such a common thing in every industry and automotive industry. It has brought out new technologies, new sensors, and so on, measuring the position in material industry, particularly using varieties of techniques, sometimes resistive, sometimes potentiometer, magnetoresistive, and every one has its own field. And today, just now we talked about how photo-optic devices have been fighting COVID on their own way, and things like oxygen meters, etc., become a kind of household instrument in every house. If you see today, they have become completely indispensable kind of sensors and their devices. And similarly, of course, the pressure monitors, etc. So, what I really want to see is they really, you can think of any sensor everywhere, and there are sensors and there are people who are working, industries which are working on improving upon their efficacy of the sensors, right? So I was telling about just now, for example, even if you consider things like the IoT systems, which are now operational in automotive systems, the self-driven cars, and so on and so forth, a huge revolution in some sense, because one kind of way to look at it is how much of this electronics, how much of sensors, how much of automation that went into a car, let us say, 1950s and 60s to, let us say, now. You will be surprised that hardly as 1 or 2% of the total cost of the car was spent on electronics sometime. And now 30 to 35% of the cost of the car actually goes in automation and electronics. And what are listed here in the big, large number of these sensors and actuators, etc. They are used for comfort, they're used for fuel efficiency, they're used for safety, they're used for many applications inside car. All of them, if you look at from the front and the back, everywhere, the car is fitted with hundreds and, sometimes there are hundreds of printed circuit boards sitting somewhere. There are processors running, microcontrollers running around. These are making things not just only for comfort and ease of driving, etc., but also bringing up a lot of new features, especially in the safety and things like that. So sensors have been extensively used in those applications. The other big field that really goes, many of you, especially if the student members here, they'll find that every sensor that you will see, I can't even go through each one of those ways, they have become the mainstay of robotics. And it is actually not something unusual that the way a student learns about many of these sensors are actually through projects, and which are mostly probably to deal with robotics in their college days. It's very interesting. And the length and breadth of the very conventional sort of sensors to some of the modern sensors, they all have nice little applications and very, in designing intelligent robotics. And those same sensors are actually find extensive applications in industrial IoT systems later. So that's very, very nice and very interesting kind of a thing, if I can say. Since we talked some time back about the sensors applications, not just only confined to you saying that, like, okay, I mean, I'm talking about a sensor and a signal processing circuit, and then the way I transfer data and everything is by certain wires. But of course, parallel developments allowed you to kind of embed sufficient intelligence, sufficient, let's say, signal processing capability inside the sensor. But at the same time, you have to build them with something like with a minimal kind of low power situations. Why? Because sensors themselves are many times situated in the field, and those need not be powered from wired power sources. Maybe they will sometimes try to kind of harness power from, let us say, solar, in which case you can't really have a lot of power at your disposal for number crunching or signal processing or using for data. So it's very important that you embed in sensors a lot of low, if I can kind of say, low power devices, but include enough kind of intelligence into that so that they don't have to transfer large chunks of data to the backend, which again requires higher throughput in terms of the communication lines. Now, those wireless sensor networks have become commonplace, just like what I told you before, in many of the transportation departments, industrial system. Agriculture is a big beneficiary of wireless systems. It's a fantastic applications in animal husbandry, animal tracking, precision agriculture, smart agriculture people saw, and of course environmental monitoring, which has become a common thing these days. Urban terrain and tracking the entire civil structure, monitoring, tall buildings. How do you monitor the structural ability of those, and so on and so forth. So just one second. And as I said, the network, the road networks, the kind of monitoring of traffic, and many applications. Entertainment, security is another major player. The healthcare, I mentioned, apart from agriculture, the next I think major industry is healthcare, and this current condition, that is obviously the most important one. And similarly, the power and as I mentioned about the smart buildings and so on. Okay, so here we are actually talking about not, as I said, wired networks, but we are actually talking about very tiny sensors, typically which are spread over a large area, and the intelligence in such that it can kind of organize themselves into your network. I'm not actually connecting, giving an IP address and trying to kind of solve how they can get collected data and transfer. And typically this is done, sensors are literally kind of sown just like seeds in a farm, and they kind of organize themselves and at some stage start transferring the environmental parameters or any sensor, whatever it's supposed to work in a field. For example, looking at the nutrition in the field, or maybe water level, maybe humidity levels in the field, and so on, and then start communicating to the nearest node, and hence ultimately come down to let us say the user, etc. So these self-organizing sensor networks are actually playing big role, especially in environmental monitoring, agricultural applications, and so on. Whereas, of course, industry or home applications, something we don't really deploy that large networks, right? So when you are sitting, okay, let me actually go here. When you talk about picking up a signal from the sensors, what you will be talking most of the time is a very small maybe a voltage signal, maybe a current signal, maybe sometimes what we call a charge signal. But that is actually our basis, which is in some sense represents the physical parameter that we are actually trying to monitor, right? But there is also this question about when I talk about the signal that is produced, as you said, most of the time the signals are going to be, the smallest signal that I'll be able to kind of measure out of the system, right? Because that is often dominated by what is the kind of noise level that I have in the system. So I can't obviously measure something below that because it is actually contaminated by the noise. There is also what is the biggest signal that I'll be able to measure by my system, because many times it depends on the saturation, the power supplies, and various parts. So that is how we go ahead and say, okay, there is certain range of system into which I'll be able to sense signals coming from a sensor. Okay, and that is what we kind of sometimes call as a dynamic range, right? So using these constraints, okay, ultimately when I do a measure a physical parameter using certain sensors, it could be very simple sensors, it could be very sophisticated sensors or transducer. At the end, no matter what it happens, always comes down to handling very, very small electrical signal, right? That is electrical because we are comfortable with electrical, signals that way. So dealing with such small, very tiny signals is always a big challenge for when you want to design very, very reliable. I mean, reliability is, of course, very important. Instrumentation system, we see that. So ultimately, why do you do all this? You process, you signal process, you design systems, design circuits, etc. What you want to do, you want to extract ultimately. Maybe I process some voltage, maybe current, maybe some charge, but my ultimate goal is not something to study voltage or current or etc. I want to do a meaningful measurement of certain physical parameter. As I said, it could be temperature, pressure, humidity, some force, or whatever this is. So when you do such a kind of overall system design, you shouldn't forget that, I mean, the main hallmarks of this system, what you develop ultimately, which actually has a sensors and signal processing together, I must actually address to a good, accuracy, at the same time, very good precision. What do they mean? Suppose I'm actually measuring a value. I mean, if you look at this graph, I'm actually trying to measure value, which is supposed to be sitting here. Okay, now when I measured using my system, the value that I'm measuring is coming somewhere here, which is of course far from the reference value, but doesn't matter. So that is my accuracy. I can't do better than whatever I told you before, because I have certain limitations to my system, certain minimal signal that I can measure, maximum signal that I can measure, and so on, and a particular sensor that I use. There is this difference between what is the actual value I'm expecting. For example, if I were to shoot, if you are giving me some gun with bullets and I am supposed to kind of shoot here, but actually I'm ending up shooting somewhere here, right? Okay, now you might say, okay, it's not bad because it's in the first ring and it's pretty accurate, right? But you're okay, but you're not actually shooting right in the middle, which is supposed to be this value. So this is the accuracy that you can kind of think about. What is the distance between the reference value, the ideal value, and what you're actually measuring? But what is even more important than that is that when I repeatedly take measurements on the same system, am I able to sit on this line like a delta function? Or is it like, that I'm actually, the value itself is varying a lot and it's making so-called the belt distribution, what quite often I think people call, or the Gaussian distribution. Obviously, the narrower the distribution, the larger the precision, and you can actually see precision nothing but the width of this distribution. So I would like to keep the accuracy to be very good. That means I want to come closer to the reference value. I also want to when you make multiple measurements, I would like to kind of see the measurements are pretty close to each other, like the way it happened here in this case. So this is very precise, very accurate system here, because I'm able to kind of shoot very close to the actual desired value, but not so precise, because the bullets are sprayed all over. But whereas here it is much better in terms of precision, but not so good in terms of accuracy. But remember, when you build instrumentation systems for strategic applications, science applications, space applications, it's very important to have both these hallmarks. And quite often, if you don't pick up the signal from the sensors well, and if you don't process the signal well by the signal processing circuits, your actual signal is lost. You can't expect to design very bad sensor and design very bad signal processing circuit and say that I'm going to take care of in the software. That's not quite often possible to do it, right? Because software can refine a little bit, but it can't really reproduce the signal well. And some of the most important thing is when you say the signal duration that you see from the sensor, obviously if the sensor duration is larger, it is easy to process, but some sensors give very, very tiny, spiky, small signals, and it is possible that you'll actually lose in your signal processing. You have to be careful. Sometimes the linearity of the sensor, I have certain physical parameter and this is my output voltage. Output voltage is linear function of the physical parameter. Then you're very happy because then it's easy to handle. But some of the sensors are not so linear. They're so-called non-linear. You have to take care of it. And the worst problems are in terms of reproducibility. When I keep using this sensor in the field, is the sensor going to give me exactly the same output signal for the same input parameter? Maybe not. It may depend on temperature, it may depend on humidity, it may depend on some magnetic field, etc. So you have to be worried about. And just like human beings, sensors too, they age with time, they age with due to many reasons, maybe due to very operation conditions, and sometimes some let us say some radiation can affect the sensitivity of the sensor. You have to worry about all these major parts when you develop an IoT system, because if you design a system assuming that everything is going to be fixed, then you will be for a big surprise, because the variation in a span of time, some of these can keep changing. So what do you do? How do you solve this problem? You solve this problem by continuously monitoring, or what you call calibrating this entire system, which includes sensors plus signal processing, so that you get consistent results and your system becomes reliable. So you can't just design a system and think that it will work the way you designed and tested in the lab. When you take it to the field, it behaves differently. So therefore, it is very important to keep checking as a part of the operation of this IoT system, and keep calibrating time to time so that you get the best intended accuracy and precision, right? So as I said many times, the signals that you receive from the sensors are very, very small, just because the sensors themselves work in the fields, and then you may or may not be able to supply enough. You don't want the sensors drawing huge amount of power to kind of bring you a bigger signal, because you also have to maintain the low power so that you can have larger systems built on a big field. Okay, so sometimes it also depends on what is the source for the sensor and what is the object that is being observed, right? So it's not, you cannot expect I'll get the big signals from the sensor so that I can process it very well. Sometimes the sensors are sitting somewhere and you have to transfer that signal to, let us say, a place where you have the signal conditioning system. So, and also many times we have this belief, right, that if you work with large systems, it is more easy to kind of process them. It's more comfortable to process the signals if the sensors give you bigger signals, right? So for all this, what is important to use amplifiers. Sometimes the sensor gives you current, so you actually use a very, this is not actual circuit, but I'm just trying to kind of draw you to the attention that if I have current, and if I want to, of course, convert into voltage, I put a resistor across it. But we don't just use a current then across resistor, because if I need to get good output, good means high gain, I have to use very high resistance. And if I use very high resistance, I cannot draw enough current from the sensor. So, but if I connect this resistance as a feedback element of, for example, an op-amp, my RF actually becomes RF by open loop gain of A, like what I've shown here. That means it allows me, like a gravity in some way, the current can be drawn from the sensor efficiently. At the same time, the RF, I can put very large value so that RF into IN, I get V out. So this very nice way that you intelligently use the good properties of an operational amplifier in a current to voltage or current sensitive amplifier. And voltage amplifiers, when the sensors give signals in the voltage like thermocouples, etc. It's a very straightforward system, of course, which we all do in our second year or first year in the lab. We go ahead and say, okay, this is inverting amplifier, non-inverting amplifier, whatever, and the gain is only decided by these two resistors here. But the problem with this is that, remember, the signal that I'm feeding here is actually like coming from my sensor. My sensor is actually creating certain charge, and depending on what is the total capacitance that I have in the line and the sensor itself, okay, that can change what is my output coming from the sensor. So which means even if there is a small change in the detector capacitance here, it is actually for the same signal that the sensor is giving, my Vin is going to kind of change. Of course, this amplifier is very nice. It is actually amplifying whatever you give in Vn, but unfortunately my Vn itself is changing time to time because of these capacitance changing. So that means simple voltage sensitive amplifiers, they're not good when you talk about signal processing for the sensor. So the best way to use, don't use the voltage, but use the charge itself. Remember, we said the sensors actually ultimately give the charge output. Pick up the charge, just like you do in an integrated circuit, put across a capacitance. Okay, so now the capacitance is the gain element here. But again, we use the same technique here. If you remember, we did not just connect charge going into a capacitance, but we actually put it on a feedback loop of an amplifier. Exactly the same technique. Here, of course, my gain is decided by, V out is decided by the charge that I'm pumping in and the capacitance that I connect it out. But the capacitance now is across the feedback loop. So the typical capacitance is C into open loop gain. Why did I do that? I did that because when I have a sensor like this, which I can represent this way, the sensor gives me current or charge, and it has certain capacitance here. Okay, this capacitance is what was affecting our voltage sensitive amplifier. But here now this capacitance here, CF, has actually become CF into A. So this CF is now much bigger capacitance compared to the total capacitance of the sensor. So even if the capacitance of the sensor changes a little bit, it's not going to affect my measurement, and I get much more reliable instrumentation system. For example, if I have open loop gain of only about 1000, and if I have a feedback of about 1 femtofarad, you look at, even if my detector capacitance changes by 10 times, okay, even then the gain is only changing by 10%. That is because of this intelligent way of picking up the charge instead of voltage or current the way you are done. Of course, most of you people, when you work in an IoT system in industry, we don't use those conventional circuits, but use what is called an instrumentation amplifier. That's because the signals that I produced in a very hostile environment in an industry, it's not a good idea to draw them by a single wire, because there is always a possibility of electromagnetic interference that happen. But if I draw them using two wires, which are typically twisted, then even if in an electromagnetic pickup, both these wires pick up, let us say, these interference together. And if I can actually connect not one, but two op-amps in the input stage, of course, by properly using the feedbacks there, I'm actually taking out the common signal, the common mode signal, which is whether it is an interference or the offset, it doesn't matter. I'm not going to kind of amplify that. What is interesting to me is on those lines, if there is an input sensor signal, which is what is the differential signal I call, that is what I want to amplify. Okay, that is done by the set of identical input op-amp kind of circuitry, and then I kind of bias it. So my gain would be, if I have like identical R2s here, and then the R1 is the feedback to common between the two, I get a gain of 2R2 plus R1 by R2. So that is the gain in the input stage. Once I haven't done that, my output impedance is going to be kind of much lower, and I don't have to handle high impedance sources coming here. And then I have completely conventional, like what we saw in the voltage amplifiers that you and me studied in the college, right? And that is a typical gain that you see feedback by itself. So it becomes a very, very useful and suitable one for when you want to interface very, very high impedance sensors, etc. Like sometimes, for biology, in medicine, for example, many of these sensors are very, very electrodes, which are very high impedance sources. Okay. Of course, many times we don't like to work with analog signals, so we go ahead and take that signal, put across a comparator and discriminator and say, okay, this is my signal, and I set up certain reference, and I would like to produce a 1 or 0 based on whether my input signal is above certain limit or below certain limit. And that is how you convert an analog signal into a logic signal. Please remember, this is not analog to digital converter, but you can call it as a 1-bit analog to digital converter because I'm only looking at either signal is up or down. Of course, the analog to digital converters do a better job here because I actually will go and look at something like a binary division. If I have an analog signal, I would like to convert. Of course, this is a very classical way of doing things, so-called successive approximation methods. So I have my input signal here, and then I have a threshold or a bias into this op-amp, which is produced by a feedback loop. And every time I ask a question, is my input signal above this or below this? And based on that, I take a next decision. Again, I convert or divide the space. This is called binary division. Again, ask a question above or below. And every time I take a decision, either I'm looking at this particular bit as 0 or 1. And that is how I build an entire string of, let us say, if you have an ADC of 10 bits or 8 bits or 12 bits or whatever, and then each time I only ask a question whether for this position in the ADC, is the signal above this or below this. Obviously, this is a nice, very simple system, but time consuming because I'm checking 1 bit at a time, right? And this is a very classical thing, which I'm sure all of us teach in the college. But then the better thing is if I want to handle very, very, let us say, high resolution ADCs, sometimes maybe for low frequency signals like audio applications are the most common where I require very good linearity because I want to get a very pleasant kind of music, very good, pleasant fidelity and very accurate, like what we mentioned. So we don't go at that time just only looking at one loop here and here, but actually I start looking at from, let us say, time equal to 0, assume that there is no reference at all. I mean, that's 0. Obviously, any input above 0 is making it, let us say, state high, and then apply to this integrator actually, and then go to a 1-bit comparator, similar to what we said for a discriminator, and then use the clock to tick to the next one and next one and next one and so on and so forth. Here, if it happens that, let us say, input signal is very small, every time I come back with the VRAP, I always get 0, 0 because the input is 0. So you get a string of zeros. Now imagine that input is highest in the dynamic range. No matter what VRAP I kind of give you, you will actually end up getting 1, 1, 1 because this is much higher than my VRAP. So for highest dynamic range, I get a thermometer of 1, 1, 1. Lowest bin, I get a thermometer of 0, 0, 0. And everything in between depends on how many ones I have will decide where my data is in between. So the larger the one, the bigger the signal and so on, ultimately reaching to a string of 1, 1, 1. This is very good system for a high, as I said, high linearity and high precision systems. And we many times use slightly different kind of ADC when we want to signal process. We actually take such kind of signals and do what is called area under the curve. We take this signal, put across a capacitor, it charges all the way until the signal is done. And after the capacitor is charged, after this signal is done, I actually discharge it through a constant discharge, like constant current source. This is constant discharge. So the amount of time the constant discharge takes to discharge this capacitor gives me some idea about how much total charge accumulated. And that is nothing but saying how much big amount of charge that is sitting in this signal, right? So while it is discharging, I actually take a clock and then keep counting the number of ticks. So the number of clock ticks indicate the charge accumulated because the I is constant here. So that means it will tell me what is my signal strength here. So this is very, very, very accurate system. And this is what is called Wilkinson ADC. But in the days of where you want to digitize signals very fast because you want to build very, very high speed signal processing systems, people don't use the so-called, what you saw, successive approximation and all that. You take all that front stage that you have of the comparator, not one, you put as many as you have number of bits of ADC. You connect them all in parallel and feed the signal parallelly. But the most important fact is that the reference that we talked about, you make it in such a way, it's a binary coded reference. So something like R into 2 power n kind of thing. N is going from 0 to the number of bits. That means I will have threshold of some X value here and 2X here, 4X here, 8X here, and so on and so forth, right? So that means my input signal is compared parallelly by a bank of comparators. My output that I'm going to get will be an ADC which is digitized in one clock cycle. All that I require is to only put some encoder here so that the data becomes available right away. Okay, and these kind of elements, which are either called flash, because in a flash you get all the output, or parallel ADC, are the main basic elements when you design so-called digitizers. Okay, digitizers are the most latest signal processing elements for not only IoT applications but also other electronics applications. So we will see what it is in a second. Okay, so for example, I think I missed one slide here, but what we normally have is that we take the waveform and then put that data across capacitor bank. So there are, let us say, 32 or 16 capacitors in parallel, and I take my signal here, and every, let us say, 200 picoseconds, I allow one capacitor to kind of sense the signal and then push to the next capacitor, and so on and so forth. So all these 16 or 32 capacitors will be holding the charge at different time scale, like a vertical slice. And after all those capacitors sample my input signal, I go back to each capacitor and say, please give me what you are holding, right? Okay, and I digitize it using, let us say, an ADC, and then I can reproduce exactly the waveform the way I have fed in the input. Many times the communication applications, signal processing applications, it becomes very important to be able to reproduce not just a voltage or current or whatever, but I actually want to produce the actual signal itself, which is very important in many times diagnosing certain problems. So these digitizers using flash ADCs or the so-called switched capacitor arrays becomes an important part of it. So sometimes when you build systems, okay, it becomes, I kind of start from a signal which is analog, but the techniques that we mentioned, I go ahead and actually build a system where the data gets digitized using analog. I don't want to process that entire thing using a very bulky digital electronics or analog electronics, because that might be very complicated to build. Can I do, especially in the applications where it is possible, take the digital data. Now it is data, right? Here it is a signal, but here it is output is the data. Now, using elements which are like, could be programmable logic devices, which we'll see soon, very soon, or maybe computation, maybe some other specific devices like DSPs. Can I do the processing digitally? Okay. And then go back and say, okay, this is now I computed, I filtered, I did whatever I like to do. And now I would like to convert back into analog, because ultimately when I communicate, when I interface to the outside world, it is again an analog signal. So you do the reverse of what you did here and ultimately provide the analog signal that is required in a system. Now, I'm not saying that this particular way of doing things in a signal processing for sensors will work in all the time. But if your system allows you to kind of process digitally rather than by hardware, for example, these systems are very, very efficient. Why? Because the system becomes very simple. I just have ADC and have a DSC. All I have in the middle is a computer or a computing element or a DSP or maybe GPU, maybe CPU. It's very easy. I can program it. I don't have to connect to wires and so on and so forth. So this is very, very nice. So these are much better paradigms of new signal processing electronics. So with that, one is now talking about, instead of building a very bulky analog systems and so on, now people say that I want to go into a microelectronics area where I want to make tinier and tinier and digital components using the same semiconductor components, which are materials which are required for other systems as well. Okay. And the best thing is when I have a bulky analog system, when I use components, the component sizes are much bigger, like capacitors and resistors and so on. And I also use wires to connect from one to another. Here, I don't do that. I actually use, because the total size is shrunk, so I actually use what you call wire bonding, which is very, very tiny bonding of components. And sometimes you can't even see by naked eye. So you have to actually do these processes under microscope, or not microscope, but the tools which are required to kind of do. But one biggest problem is when you shrink the component sizes to smaller and smaller sizes, some of those which you didn't bother out before, some of these intrinsic circuit properties. You take a resistor, and if I give a resistor to you, you will say, it is 50 ohm resistor. Okay, great. But if I give you a 50 ohm resistor, which is extremely tiny, you must also consider that resistance has a, let us say, capacitance, intrinsic capacitance. It has a small inductor, which you happily ignored when you work with big components. Now, if you operate these components at a higher frequency, then these intrinsic circuit properties create a big hell. So you have to actually take care that when you shrink the component sizes, you also have to worry about how to take care of those intrinsic parasitic properties, right? And that is the big challenge for a microelectronics design engineer. Now, when moving from analog, so far what we talked about, when you talk about digital circuit and especially going into miniaturization, but overall, if you talk about a building block, you're actually talking inside, as I said, a wire that you want to connect from point A to point B. You want to use so-called gates, which are combinatorial circuits. So I take so many inputs into an input of a gate, and the output is instantaneous because based on the status of inputs, I'm actually seeing instantly. Of course, the only input to output delay of the gate matters, and this is what I have at the output. In the third category, you have so-called sequential circuits, if you like that. They operate by a clock rather than asynchronous. This is asynchronous. I give certain inputs and my gate output will be right there. But whereas here, if I talk about like a flip-flop, for example, if I feed it data here, I require a clock signal here to move the data from the input to output, right? Okay. So these are sequential circuits, and these are combinatorial circuits, and this is just wire from point A to point B. No matter how complicated digital circuits you build, it's very likely that they will fall under one of these categories. There are hardly any other category which is not a sequential and which is not a what you call combinatorial circuits, right? So sometimes we go and use very simple circuits which are in the market, whose truth tables are decided by the manufacturer. They're very cheap because a lot of such manufacturers produce the same chip, maybe Texas, maybe Motorola, maybe somewhere else. But the main idea is they're very general purpose. The truth tables are decided by the manufacturer. But sometimes when you build a very big signal processing circuit for a huge IoT system, you don't go to market and buy these chips and make such a big bulky circuit, and they will be drawing a lot of current and so on. You will say, no, I would like to design my own IC. Here you are a user and you are the one who is designing the chip, not the manufacturer, right? So that is what is called, specifically for your application, you are actually producing an integrated circuit, right? This is called ASIC. Sometimes something in between happens. Like suppose you and me are the manufacturing industries for, let us say, modem circuits, or maybe communication equipment, maybe audio or video equipment, or maybe computers or whatever. So what do we need? We require a set of chips which are not very general purpose, okay? But at the same time, they're not very specific. If you are a modem manufacturer and I am a modem manufacturer, both of us will end up using maybe the same chip that is produced by one company. So there are a limited set of companies which produce specifically components meant for certain industry, right? In this case, for example, as I told you, a modem or a communication equipment, etc. So these are, yes, no doubt, they are meant for specific application, but this is more for standard products. The products could be communication or VLSI or or entertainment or industry, whatever. So this is something which will lie between the standard products and ASIC products. These are application specific products. Okay. So all these kind of things you might need to kind of use. So as I said, if you have those standard products, there's nothing wrong about it, because you can put so many of those circuits together, connect the output of one into the output of other. And if you can do wiring the way you like. But the problem is that if you make very big complex circuits using those standard logic, it becomes very risky to develop complex system. And sometimes if I want to make correction, if I want to make an incremental development, it becomes difficult. So therefore, now we talk about what we call programmable logic circuits, where it allows you to take the process signals from sensors, and then whatever intelligence that I want to put in, whatever logic that I want to put, whatever Boolean algebra that I want to put in this circuit, they're not like logic gates, which we have used before, but I can actually program them in the field. So that will allow me to explore new architectures and also, new functionality that I can kind of build in the system, right? Programmable logic arrays as a general paradigm, but more specifically, the so-called the gate arrays, which can be programmable in the field, in the industry, in the college, in the research lab. These are called field programmable gate arrays, right? Whose truth tables or whose logic is not decided by the company, but decided by after the manufacturer has done it. And then when I buy the market, they of course come as you can say like a white canvas, but I'll be able to program it with the new features, new functions, maybe new standards. And if I don't like it, I can reconfigure it with the new logic every day I like. I can make a product in which I can use field programmable gate arrays. I can deliver the product to you. And then if you allow me to access that product sitting in my office, I'll be able to kind of upgrade, for example, the product features and so on. Of course, obviously, the advantages are brought by programmability of the chip, right? And the way the chips work, of course, is I have the basic, building blocks in terms of the logic blocks, where I can put any complex Boolean algebra inside. And then once I would like to connect up from one block to another block or another block, I have lines which are also programmed. So it's not like a wire which is manual and which is fixed. I can actually sometimes connect from A to B. Sometimes I can remove that B and connect to C and so on, right? Those are routing matrices, which are also allow me to kind of add a programmability into it. And ultimately, I want to bring all these outputs into my chip pins, right? The chip is sitting on a PCB. So I should be able to take inputs and outputs into the chip pins. So all these three elements, the logic inside, the routing inside, and also bringing the input outputs on the pins, they're all programmable. So that's why this is, of course, field programmable chip, right? One simple example I want to give you is that if I want to implement certain logic function like y equal to a and b or c, right? You go ahead and simply make a truth table out of it and they say, this is my ABC and this is what I expect my output to be y. There is no issue. You take this truth table, put it up in a what you call lookup table, right? Lookup table is a kind of memory cell in which you put all these, let us say, 8 various truth table elements. And then if I give ABC here, of course, the y will produce automatically because it actually like a circuit of ABC addresses a certain cell. In that cell, my y is already written, that y comes out. Now, tomorrow, somebody says, no, I don't like this y equal to a and b or c, but I would like to have y equal to, let us say, a or b and c. Now, in a typical circuit, you need to kind of essentially desolder everything and connect it and use another IC and so on. Here, you make a new truth table and kind of download that truth table here, your circuit becomes simple. So that is how the functionality of that. And since I told you that you will be able to kind of program not only what goes in each of these logic cells, but you could also program the way they get connected to each other. So that programmability add to the functionality. And then the entire operation of this circuitry is what is decided by the interconnects that I told you, which are programmable, right? But that programming technology itself, there are a few technologies that can work depending on what constitutes your system. You might use so-called anti-fuse technology, which is something analogous to like the way a fuses works in an electrical system. You connect or disconnect between two wires using a fuse element. You can either make it 1 or 0, or I can program, let us say, switches like this, where the inputs are connected on source. Maybe the outputs get connected to various lines, and I program the base either with a potential that makes it or disconnects each other. The best technology also is that if I have logic cells which are placed like this, and these are my routing matrices, in the routing matrices is like a static RAM. I either write or 0 or 1 in a RAM bit will connect or disconnect one cell to another cell. Now, these are obviously volatile. If I switch off the circuit, the RAM will lose the contents. So therefore, again, I have to kind of download what I would like to put it into this interconnect switches. That is not a problem with the anti-fuse or flash, but this is kind of volatile. But then this is much faster compared to this technique. So you have to actually choose which particular technology that you like to use. And these chips also provide you with, let us say, soft processors. What do you mean? Just like microcontrollers, you are able to program outside. Apart from giving you flexibility to program or change the hardware logic, you could also have actual microcontroller like devices sitting, soft processors sitting in the FPGA. You can program it just like what you do for 8051 and so on and so forth. And depending on what is the manufacturer from where you buy the FPGAs, they come up with their soft processors, and they're exactly similar to how you do programming. But some of you who don't want to do this programming yourself, you would like to import the standard processors like ARM Cortex or PowerPC, etc. They can also come as hardcore processors, right? So depending on which technology, interconnect technology you want to use, or what is your requirement, you will actually end up buying a chip suitable for you. 90% of the chips in the market are produced either by Xilinx or Intel in this case. What is the best in this case for especially the younger members is, since the programmable logic actually chip comes to you as a white canvas, as I told you, it allows you to develop a large number of applications. Doesn't matter what they are, protocol generators, calculating circuits, DRAM controllers, big blocks of memory, PCI control clock. I mean, there is no limit on what you can do. What is nice thing about it is you can take the specifications of a chip that is produced by a company, you develop applications like on that. That is a property owned by you. It is an intellectual property owned by you, which you can actually sell, which you can share, which you can team up with a product manufacturer or IP manufacturer, or the FPGA manufacturer. And you say, look, I have developed these IPs for you, which cost this much. But the best thing is that when you use this chip, you don't have to do firmware development by yourself. I already done it. It will allow you reducing the power. It will allow you reducing cost, reducing the time to market, and it will improve the reliability because I already programmed for you. I already built this application for you. All that you do is you buy from me and just put it and use it and so on. So people like this because this is a property, an intellectual property owned by you, and you don't require a big investment in order to become an IP core developer. Okay, so this is a very nice opportunity in this industry. And many times even the FPGA manufacturer allows you tools and the reference designs, the development kits, the evaluation kits, and so on, and the basic EDA tools available for you to be able to kind of develop such systems. Okay. Of course, you're required to kind of know some of the hardware description languages like VHDL or Verilog. Some of them are actually taught in the curriculum. But what I really wanted to tell you is that nowadays people don't do so much with VHDL and Verilog, and actually they use a system called high-level synthesis called HLS, which is much easier to kind of able to kind of develop APIs and applications for FPGAs. For example, one of the application called Vivado by Xilinx is the so-called HLS system. So these are of course very classical development paradigms, but people are now spending, they are using more and more of the high-level synthesis work. Okay, just one word I wanted to kind of give you a feeling about it. The way the digital technology, the way the programmable chips that I was talking about are going in, and the sizes of the chips in the microelectronics regime coming down is because one of the big technology that happened is in the fintech, FinFETs. In the regular FET, you have a source, a gate, and drain, right? That is how we operate, but which are essentially a single dimensional element here, if you look at it. But if I can actually modify the gate to be, instead of single dimension, suppose I make 2 dimension or 3 dimension, or even maybe 4 dimension, which means all around, I'm actually increasing the current density from source to drain, which will help me to switch on, switch off the device much, much faster, right? These fins, like, what you have for fish fins are around the gate, is actually helping the current switching or the chip switching or transistor switching very, very phenomenally. So that is why this is called FinFET technology. Way back in year 2000, set of guys from California, University of California, worked on it, but many industries latched on it. For example, even 10 years ago, 20 years ago, you had the so-called omega, which is a 3-dimensional, because omega shape of the gate, it actually gave less than 1 nanosecond transition times. So amazing kind of devices, and Intel and many other manufacturers got latched onto it. And so today, all the chips that come about, they do use FinFET technologies. For example, the Xilinx chips that you have, so-called ultra-scale chips, coming out with. You remember I told you about those lookup tables in early 80s? They were only about 64 flip-flops in an entire FPGA. And today you're talking about billions of them in one chip. And what is even more important, if you remember, I talked to you in the context of sensors, you need to not only acquire data, but you should be able to transfer them at higher speeds towards the data processing element. These FPGAs nowadays come not with just so much of number crunching or digital data acquisition, but the data itself can be transmitted from the chip to the backend at about 30 to 40 gigabits per second, and not 1 or 2 links. You can have hundreds of such communication links. So that means you have that one big, you can say, a chip which takes up, as much as the sensors that you want. They have fantastic amount of real estate on it to do your data processing, and they can actually communicate very, very fast at the back end. So that means the entire system becomes very reliable, at the same time becomes very efficient. So even from an area where earlier, multiple digital blocks were actually parallel, like a parallel processing, were doing and exchanging data between each of them and number crunching, ultimately coming down. Now that is all replaced by one chip where I feed the data, data comes out, because all that was included inside is due to the communication links, very high speed links, and all the data processing that happens inside. So that brought us to what is called developing a complete IoT system with, except sensors, everything else is built into one single chip, is what is called system on chips or multi-processing system on chips. Here, if you look at one of these chips by Xilinx, so-called ultra-scale chip, which is again at about 16 nanometers FinFET technology. You look at here, I have all the processing elements that you can think of, whatever you want, Cortex, processors or any other processor you want me to put it. I'm already having it. I have all the memory structures sitting there, huge memory structure for data processing. And I have all the, what you call system functions. System functions could be timers, it could be clocks, it could be DMA, it could be monitors. You name anything, they're all sitting there. Every possible interface from this chip to the external world, all the way going from USB to gigabit chips to CAN bus to UART, SPI, you name any of those interfaces, they're all built in inside. So all that I have is, I have to just take care of one particular chip into which everything can be built in. And if you are a technologist where you develop applications for RF instead of signal processing. You could also have in one chip, the 64-bit, 32-bit, doesn't matter, the processors. And as I told you, hundreds of very, very high-speed transceivers. And you have not one, not two, you have bank of ADCs and down converters. You have banks of, let us say, DACs and down converters, up converters. You have all the basic elements that are required to develop any application. It could be software design radio, it could be microwave applications, it could be anything that you want to develop in the RF regime. You remember olden days, we used to have the RF microwave circuits, which used to be extremely bulky. And one of the most important thing to take care of is, as I told you, the inference, the crosstalks, and I mean the noise, and it used to be terrible, like having a very bulky system. Now, if you make it miniaturized, all those interconnections are gone with one. So it becomes a very efficient and very, very cost-effective kind of a system. And in the IoT systems, which requires applications mostly in the agriculture area, you end up actually monitoring, let us say, both the, if I can say, holistic parameters as well as the individual component parameters. Now, holistic, I mean, you may be looking at the, let us say, the land parameters. I want to look at the water content. I want to look at the nutrition in the field. I want to look at the quality of the soil. Is it hard? Is it soft? Is it, all those parameters where, of course, you will have literally thousands of such sensors sitting in. But I also want to monitor as a kind of structurally. I also want to look at, let us say, what is the height and the width and the volume of a plant? What is the kind of, sometimes the component layout of a leaf? Is it curved? Is it straight? What is the temperature? What are the, the structure of the plant with reference to time? If I want to monitor temporal, you call, no? Temporal is with respect to time. How is the growth that is happening? All this information that comes to you as bits and pieces, because they're individual sensors looking up for different parameters. Now, when you want to build as an overall system, you're not talking about one sensor and one signal to look at, arrive at a parameter. This is where each sensor requires a different signal processing techniques, because each sensor is not same. I mean, some work in one principle, some work in other principle, some gives you data as a current, some gives you voltage, some gives you across 1 mega ohm output impedance, some may give 1 kilo ohm output impedance. How do you kind of manage to bring a big IoT system using varieties of sensors, and that too, not one or two, a large number? So that is where, as I said, more and more of the signal processing techniques and the VLSI in some way of the circuits have come in handy to make a very compact kind of system. I also talked to you some time ago about not just agriculture, but typically applications where you require to monitor large spaces like animal husbandry, where the cows, buffaloes, goats, sheep, whatever it is, they are grazing over literally, tens or hundreds of acres. How do you actually monitor them? Okay, so there have been the advances using both in the sensors as well as the signal processing. They've become very, very efficient way of system. For example, if I'm looking at a vast field that I want to kind of monitor, can I kind of look at, instead of using drones and, for example, I think I may have here, in a big field like this, can I use, for example, this is the kind of ingenuity, it is a kind of creativity that people are going about. Here, there is a big field and there are these transmitters, and you actually build very, very tiny signal processing circuits which embed not only the sensor here, but also the the electronics, everything is kind of built in here. Just let me see why I'm not getting this. So can I actually mount this entire system on a back of a, let us say, a bumblebee or a honeybee? Okay. Now, as the bees fly around, can I actually collect the data from, going in the field instead of using drones or using some other application? People are going to that kind of level. But what is important is to be able to mount on this, the bee require this entire electronics and sensor, etc., to be very, very tiny, and they have to consume very little power, and that is the way by which you will be able to communicate. But that will also bring a system like how do you collect data? So you may have these devices which are actually, it's like in some like a GPS, you get connected, you can also measure them, you can also get their positions as they fly off, of course. This is easier task, but the task that you are talking about is if you want to collect data from this sensor to be back, I actually transmit an RF from each of these transmitters, the data received, and I put data back on the same RF. My data size is not very large because I'm only talking about maybe some local parameters there, and which can be transmitted very easily. That is why it is important to have low power devices and a good communication technique. So here people use what is called a backscatter communication back to one of these stations. And if I have several stations which are lined up in a huge field, I'll be able to kind of collate and collect this data. This is, you can think it of as a proof of the principle, but people are working towards those kind of new technology areas. Similarly, in the field of medicine, people now gone are those days where you look at use sensors. I mean, they're not even sensors in some sense of, the X-ray films that we all have gone through, the X-ray film that we use to take a picture for a body, bones or broken bones or some structure inside. They were essentially black and white or a grayscale. Now people want to use sensors which are based on semiconductor materials, silicon, for example, sensor, but it is not like just a film which will only distinguish black and white or a grayscale. You kind of look at the sensor, the X-rays that are coming from the gun to the patient and get onto this chip, but the chip is only sensor here. And the signal that you will see in the next slide is not just one signal coming from one sensor, but the signal is split into cells of about 50 micron by 50 micron. And there are 256 by 256 pixels. This is huge, high resolution pictures that you will get for every single signal that is produced in each of the sensor chip, which is segmented, right? Now, if I add some, and you can actually see those matrix here, and then each of those signals are actually going and getting processed through semiconductor chip electronics, which is just padded right below, right? And the inputs are kind of connected. You remember I said the wire bonding? You can't even use normal wires because this is extremely small chip that you work on. Okay, so therefore, if a patient has taken an X-ray and then the X-ray is coming through the patient falls on this sensor, and each of those 256 by 256 cells, they will have their own amplifier and a comparator, a counter, something like what we described, and that is for one pixel. Like this, you will have 256 by 256 pixel, and you can really imagine if I can process the data for every, it's not single X-ray energy, but I'll change I will actually scan, you can say, the patient very, very quickly by multiple energy sources. Then if I can accumulate the data that is collected from there, instead of seeing the patient X-ray just like a black and white or a grayscale, I can actually look at the patient data at a molecular level, and I can actually look at, it's like a pages in a book. I can ask the system to give me the patient's internals as I look at, as I want. I maybe want to look at water in the body. I want to look at iron in the body, maybe gold in the body, or molybdenum in the body. Whatever I like, I can actually get a very, very high resolution color coded pictures. And that is what helps the patient, the doctor, to be able to diagnose problems years ahead of the patient is going to kind of. That is the kind of sensor technology that you can imagine, which is now going into the medical field. The same, which is also applicable for other fields as well. Okay. Similarly, as I said sometime back, today for the COVID, we use varieties of instruments, varieties of sensors, which are working out on the optics essentially, right? You look at the patient's parameters in the optical domain. For example, many of these so-called photo detectors or photo sensors are working out in the so-called real-time PCR, antibody testing, X-ray and CT imaging, which we just now talked about, digital pathology, and many other broader research applications. But they use these sensors, which are sometimes not meant for medical, but during the COVID, as I mentioned, suddenly they could change their application. They could change the technology more adaptive to COVID and other, I would say, biological applications. So this is a very interesting way of looking at the technology. One of them, many of you must have actually seen. For example, if I want to monitor somebody's oxygen level, the way we use, all that requiring is an LED that is actually emitting the light, and then the photodiodes, which are determining how the red blood cells that I have in the body, what frequency or what wavelength of the light that they absorb. For example, if my blood cells have good amount of oxygen, they will be absorbing more infrared compared to red light. Okay, now I'm actually my photodiode, which is very tiny, sitting in this device, is actually monitoring this, and then I'm able to kind of quantify and say, okay, your blood cells are having maybe, let us say, 90% oxygen, 85% oxygen, 97% oxygen. This is a simple sensor which has been conventionally used in many applications, but able to kind of come up and build a device out of it, build a useful device out of it, which can be, worn in on a wrist, just like you wear a watch. And now, having said that, you don't have to only talk about oxygen. You can actually measure many other parameters by pulse. You can measure by oxygen levels, maybe BP or whatever it is. This is how you kind of package from a basic sensor device and how the signals get processed and then become an application-oriented thing. That is how today companies like Apple or Fitbit or whatever, they all of them have latched onto this thing, and millions of such kind of devices, which are essentially the field of IoT in the world, can benefit from the data. So the data that is collected from one patient is not just only used for that patient. The data that is collected from one car that is being driven on a highway is not just only used for that car, how to move forward, how much time there, but the data obviously is instantly shared by the backend to all the systems in the world and all the patients in the world. So therefore, you are able to get benefit out of it, because the data analytics working at the backend is able to kind of say more accurately what is the current situation of oxygen level, or what is the current situation on a highway, and so on and so forth. And that is something which is driving a way into many medical applications. Today, you talk about sensors which are not just only physical, like mechanical sensor, microfluid, etc. Not just only biological or microfluidics and medical implants, or sometimes very microsurgical tools and so on. And even some of them are also, when you talk about microfluidics, even the chemical or gas, and those sensors have become very important. Now, today you're reaching to a level where the medicine dissemination, medicine dispensation into a patient went to a level of where you talk about a small capsule-like device, which comes with its own antenna to communicate to the outside patient, the system. You have the battery that is built in inside. You have all the electronics components required to function it. And these micro reservoir, which is into which you actually, the medicine is swallowed. And then at a given particular time, looking at the parameters of the patient, you want to inject exact amount of certain medicine, let us say through this so-called micro needle. This looks like almost like in some sense, what do you call, scientific fiction, but these are realities today. people use magnetic membrane sensors where you have a drug which is reservoid there, and depending on the magnetic field that I apply, the amount of medicine or the drug gets released very, very accurately and very, very pointedly. So therefore, it's not like taking oral medicine. By the time it reaches the affected organ, the amount of medicine is, actually is very less. So I have to take a much larger dose of medicine. But here, if I'm able to kind of deliver the medicine very precisely calculated way and with time. So because it's very impractical to look at that somebody takes insulin every 5 minutes or 10 minutes. It's not possible. So you take morning, evening, or afternoon, or whatever it is. But here you time it well, you can monitor it well, and you can also exactly calculate and then keep them. So it's a complete sensors, signal processing, and actuators, and all of them working together. And that is what is bringing value to the patients. Of course, even in the sensors, we all just now talked about the semiconductor sensors, which are used for the body scanning. But now people go to the next level of so-called. See, this is how the technology is dependent on the science that is being done in the back door. So there are scientific research about this brand new material called, not so brand new, it's already happening, called perovskite, which is much, much easier, much better than the X-ray films. Okay, they can be, if I have a certain device, I can kind of deposit just like, spraying of the solution. And then that will keep a very thin layer of this material on it, which is much cheaper to produce large areas of sensors. Okay. So this is very rich. The perovskite is very rich in heavy elements. So like lead and so on, and iodine, etc. So X-rays in the detectors like semiconductor, which might be passing through undetected in other materials, this will get detected. So as a result, these sensors now are actually able to perform the conventional silicon detectors, which are especially when you use them on X-rays. And what is even more important is that these sensors do not require any bias, any power source to make them work. Okay, and they're much more sensitive than most of the conventional devices. So you can see, while people are working with sensors and sensor signal processing and IoT system, connecting up big data, analytics, etc., there are also set of people who work in the basic material science, and which will bring more efficient sensors, more tiny sensors. Here we are talking about one of the biggest thing is to look at it is the power source. The larger the sensor takes more power, it becomes difficult to build big IoT systems. But here you're talking about sensors which do not need intrinsic power source. So those are kind of things that happen. And there are a set of people like even IEEE works on the so-called smart sensors, where the signal is not only received, but you embed more or less all the signal processing circuit, as we said, in the chip, only spit out the data using conventional interfaces like SPI or whatever standard output. So if you want to interface them, if you want to communicate them, if you want to bring protocols, develop them, you don't go and use the same conventional interface devices, which are like, RS-232C or SPI or, whatever those lab use and so on, which are not meant for using in a low power, low weight devices. So IEEE comes with a standard called IEEE 1451, which is specifically meant for signal processing from the sensors, the way we are working on. So these are all multiple developments that happen in parallel. So you don't, in a conventional thing, you take, if I have a big field where I have sensors, then you pick up each of those sensor, make an interface, and then because you don't have so many ADCs, maybe you multiplex them, take into computer, and then if you want to give some action as an actuator, then you kind of bring it and so on and so forth. Some of the smart sensors don't require any interface. You can see this smart sensor goes straight to a data multiplexer and so on and so forth, right? So those are the kind of newer developments. And of course, nowadays, sensor processing has become a little bit easier because in the market, you get lots of very, very few hundred rupees worth microcontroller boards, and even the FPGAs that I talked to you about, they become, if they are smaller FPGAs, they really cost nothing. And you don't have to even connect these wires, because now you have Node MCU which are able to kind of transfer them wirelessly. This is very nice because this gives opportunity for students to be able to play with the sensors, able to play building systems, even at the school, so-called mini projects kind of level, etc. This is very nice, and it will also make them introduced to various interfacing techniques, programming techniques, signal processing techniques, etc. This is, I think, something quite nice. And as I said, at the end of the day, it also is important, since the sensors, electronics, and actuators, etc., are all made by same material, namely semiconductors, and particularly in silicon. So now they are actually trying to merge, trying to integrate all together into one piece. The advantage will be, it will be a very reduced size, because I'm not interconnecting with each one of them. Low power requirement, much faster that I can kind of make the systems happen. And what is more important is, if I interconnect, then there is always a possibility of an electromagnetic interference, right? That I can avoid if I can put them together into one integrated piece. And so that means I can develop much better signal to noise. And what is even more important is, when you make chip together, then there are no integration steps involved. You don't say, first please make chip, then I'll test it, then I'll go to develop independently the signal processing circuit, then I'll connect communication circuit, maybe something else. But if everything is made on one table, essentially by one foundry, then it is much faster to market, design to market kind of thing. So it's and at the end, I think it costs less, right? Because there are not multiple operations involved. So this technology integration, which is now going in a big way, I think is something which one has to latch on, especially the students. I must say that now people don't talk about them as a vertical alignment, vertical components, but they're all together working as a single technology integrated kind of thing. So I want to really go a little bit fast, just to say that when we want to shrink the so-called node sizes, as I was mentioning to you, the best thing that happens is that, typically what we study in the school, the resistance, the length and cross section of such devices, and the resistivity. Resistivity is the material property. So what is happening, what is interesting is the so-called ratio property of planar resistances. If I have, it's like each of them you can consider as a kind of a transistor inside a big chip. All that kind of requires is that if I use the same thickness of the material because of this relation, and whether I kind of shrink or compress, just like taking a mouse and zoom in or zoom out, I'm actually changing the length and breadth proportionately, but I'm not changing the resistivity, I'm not changing the thickness. And you will actually find, if I want to understand between one node and to the other node, the ratio of the resistance are going to be remaining the same. So which means that I can start with some, let us say, some 250 nanometers technology, and I can just change the ratio of this property, ratio of this each element, then I'll be able to get maybe 60 nanometers, maybe 30 nanometers, without really changing anything, any property of any chip. So of course, what comes to play is, can I take a big a transistor of maybe 250 nanometers, and if I want to inscribe a transistor which is only 16 nanometers, the so-called optical lithography, by using which you actually etch these transistors on the wafer, becomes also important. So the technologies which are coming from, which are again going in the laser and material science, is coming to play, and then that is what is helping to kind of shrink your chips. So starting all the way from 1960s, where the chips were of the order of maybe 50, 60 micron, and today around that we are talking about few nanometers, 10 nanometers, 6 nanometer technology. This was only possible because of the optical lithography advances that happen in that technique. And if you really see today, if you Google out, you'll find the race to make the chips even smaller and smaller, integrate the technologies to even more and more high level. You'll find, way back just in September last year, one is talking about 10 nanometer device by Intel. Early May this year, IBM talks about 2 nanometers. And after 10 days or 15 days, TSMC talks about 1 nanometer technologies. I mean, you can really see the race for making faster and faster and smaller chips and using varieties of technologies. 1 nanometer is almost like the absolute, minimal theoretical energy barrier that you can have for transistors, for electrons to be formed in semiconductors. You can't go anything less than that. Okay, so that is the kind of technology challenges that one goes for it. So, as I told you, that how long one can go in these shrinking sizes. 1 nanometer, I mean, it's almost reaching atomic levels. You can't go anything less than that. You can't really go as per the Moore's law, like going up to every 6 months, doubling up the densities and so on. So what people are now saying is, can we, for example, build what is called, instead of 2D IC, which is like a planar space wafer on which I etch thousands and lakhs or millions or billions of transistors, that's fine. Can I actually build on top of one layer, another layer, and so on? So these are like tires, if you can call. So if you're able to do this, so instead of one chip having only one layer of wafer, can I have multiple layers, multiple tires? Okay, what is the advantage? Of course, now if you build one more, the density get multiplied by 2. Maybe if I do 3, maybe 3 times. But the problem is, I should also be able to build one layer here, and I will be able to work on the top of this one another layer, right? So how do I, when I work on it, the temperatures that are caused for the second layer should not affect the structures that I built below. Okay, that is one problem with semiconductors here, because silicon requires higher temperatures. But people now found a way to use the so-called non-silicon technologies, where like a carbon nanotubes, etc., can be used, and that can be operated at a higher, lower temperatures. So you'll be able to build multiple layers one on top of the other. So these 3D integrated circuits have been now in kind of the new thing, and they are able to kind of work on building very, very high density chips. Of course, when you build one layer to another layer, the point is that I should be able to connect like wires in a printed circuit board. I should interconnect the bottom layer to the top layer to the middle layer to the top layer, and etc. So that is kind of done by building such kind of cavities and filling up like what you do making a wires in a printed circuit board. But you will be surprised to find, if you do such thing in a chip, the amount of tungsten that is required to connect from one to another is hundreds of kilometers, which means that you will waste a lot of volume surface connecting up these bottom to top layers. So people found that what they call cap fill process, avoiding those thick layers of tungsten, and we are able to increase the kind of density to almost 40-50%. So these are super advances that happen all the way in the material science, and as I said, laser techniques, etc. And then using these kind of techniques, one is able to build very, very high density, very reliable signal processing circuits, right? And the thermal management is another big story. For example, nowadays, instead of getting the chips which are with lids, when you go to market, you buy a chip, it has a lid on the top. Now, the point is, if the lid is already there, and if I want to do a cooling of the chip, it's becoming very difficult, because the chip, like what I told, system on chips come with very, very high density with a lot of power consumption. Can I actually bring the technique where I remove the lid from the top and then deliver it as the chip as a bare, so that I will be able to kind of draw and make the system in such a way that I build the, like a shield, a thermal insulation, or I would say heat sink on top of that. And I can quickly draw away the heat that is produced in the chip, sometimes by heat pipe, or maybe some vapor channel, or sometimes even people flow liquid through the pipes to draw the heat very quickly. And then, the industry went one step further and said, look, I mean, this is your chip that I'm producing for you. Can I put a very small, microfluidic small channels which are already embedded during the manufacturing of the chip. In which case, you can, when you use the chip, you actually flow the liquid or coolant, whatever, through these pipes, and that will give the best possible thermal, taking away a thermal management system in some way. So, these are the advances that happen, one oblivious to the other one. And that is what today you'll find systems are getting more and more and more efficient. So I just want to kind of conclude by saying the sensors and the signal processing, which we discussed today, are the most crucial components, not just only for the IoT, the electronic systems that you see. And today, IoT in general owes a lot of its growth to both of them. People, the sensor development as well as the signal processing development. Besides that, many times I mentioned to you the advances that happen in material science, microfabrication techniques, which are shrinking the sizes of the chip, very, very low weight signal processing architectures, which are sitting inside the smart sensors so that they don't consume too much power, but at the same time do useful signal processing, and self-organizing sensor networks, which I described, where they can organize themselves in the field automatically and pick up the signals from the field and then send to the nearest cloud. These are the ones actually fueling the growth, both in the manufacturing as well as its applications. So the IC industry itself, I had briefly mentioned how these newer and newer technologies, 3D ICs and many other, some of them I had to skip because of want of time. And so that is kind of brought continuously syncing the device geometry. And of course, the functionality is increasing every time because you make the field programmable chip where the functionality is decided by the user rather than the manufacturer. The microelectronics technology, which are also independently making good progress, and they are also finding new applications. Just now, a couple of examples which I gave is in the sphere of medicine or agriculture or imaging applications, etc. Just only one such thing. Okay. So if you want to continue in this field, the historical growth that happened, the semiconductor industry will require, once again, advances not in just one form. It could be front-end process, it could be lithography, it could be design innovation, it could be performance processors, architectures, thermal management, which I mentioned to you at the end. And nowadays, most of them are, even in the VLSI regime, they are not talking about multiple chips. They're actually talking about putting everything on one chip, the so-called system on chip technologies. So I think those are the directions in which the VLSI is heading. Those are the directions in which sensors and signal processing are heading. And they're very interesting because they also bring up a lot of opportunity to both faculties and students, industry, and also, of course, a lot of R&D that's happening. So with that, I would like to end by thanking you. Thank you very much for your attention, patience.
Thank you very much, sir. Any of the participants are having any questions? I request them to please ask.
I see.
Good afternoon, sir.
Good afternoon.
Yeah. So there are two questions which are on YouTube. Can I ask on the behalf?
Yeah, please. Yeah, please.
So these two questions are almost related to each other. The first one is how to reduce the gap between industry and academic, from Dr. R.S. Khan. And the second one is from Dr. K.G. Savarkar. What topic to start if you want to integrate Industry 4.0 in the academics? So basically the question is related how we can integrate both the things.
Yeah, of course, this is a very pertinent question, and question that is so relevant to the FTP program that you are organizing. I also touched upon this fact that there is this fine, thin gap that existed between. Sometimes I also talk about the so-called research possibilities, research problems, what can be tackled in the academic institutions on a separate topic, that is. But since this question is, See, the point is that academic institutions' main job is, let us say, if I can say that, is more in the teaching and more in the academic field. So intrinsically, the institutions there may or may not have the required ambience and ecosystem or equipment or sometimes even funding to carry out research the way sometimes I described during my talk, which is more sort of things happen in R&D institution. But having said that, it's not that the academic institutions cannot become part of this excitement. Some of the problems that, especially, for example, today I talked to you about AI-based systems which uses the data from the silicon sensors or computed tomography systems, or the systems like where nowadays we talk about patient has this much percentage of infection and so on. How do you quantify those? You quantify those by using the image processing systems, which are in some way learned from the known image. So, of course, you people know like neural networks or AI techniques, basically machine learning or deep learning techniques, where if I have this database, which is many times you found, that is why I said it's a collaborative work that is happening in the field of COVID, is can you build, for example, a simple network, and can you train your network to be able to kind of identify, that is classification in some way, just yes or no kind of information. And can you also quantify? Can I actually look up by training my network and by saying each element of certain either linear, which means aerial kind of thing, two-dimensional, or a volume, because our lungs are in some sense is a three-dimensional object. It's not two-dimensional object. So can I say quantify and tell that, okay, this fraction of, so there is a lung that is sort of given there, and I'm able to localize their boundaries. On top of that, there are, let us say, certain patches which are occupying certain fraction of the space that I can look at it. So that means that person is having a kind of score of some number. Maybe let us say a score of 30% or 40%, whatever. So that tells a certain severity of this patient. Now, how do I quantify? How do I calibrate this thing? That is where you have millions of database available on ordinary X-ray, chest X-ray films, which are available. In fact, you find now, if you actually Google, you will actually find even the neural network structures, which are, maybe 100 layer, maybe 120 layers, very complicated part, but which are available for you to work on. The entire framework as well as database, training samples, they're available. Can I work on those and look at, putting up some kind of novelty that I can add from my scientific ingenuity or academic knowledge, and then you can build those kind of systems. And this is just mathematical modeling, for example, mathematical simulations, Monte Carlo simulations. These are problems which are today every industry looks at. Every industry want to look at, if I'm building a big bridge or a roadway, is there a way somebody can actually mathematically model it and put all those conditions through which this the bridge is supposed to survive, let us say trans-ocean link is supposed to survive. Can you mathematically model it and simulate it and put all those conditions on their external hostile conditions, basically, and validate this design that it can actually sustain? These are all simulations problem, mathematical modeling problems, or learning systems problems, classification problem, image processing problems. These do not require a big infrastructure. And this is the best way to connect up with, if you start working and if you connect up with other people, they'll be kind of able to tell you that, okay, can we collaborate? Can we really work together? I think one has to choose these problems which are suitable to a particular organization. Like some of you might be good at certain field, so pick up only those problems, and that is how I think one can get in. There is because your 70% of the time probably goes in academic teaching and so on and so forth. So it becomes a bit tough to kind of do a full-fledged R&D while you're still making your busy life with teaching. So this is the best way to make a bridge between those. And your students, when they see you working on these problems, they will also get excited, and maybe they'll pick up some topics into their project. Maybe you can give a part of that problem to as a project to the student. And this is how you inculcate the research culture on the campus.
Thank you very much, sir. There's a question from our Deputy HOD, Dr. Poonam Sonar. How to tackle security issue of the sensor in IoT? Yeah, actually, this is a very, very pertinent question. Remember that we are driven by one strong push that you want to build, let us say, all the way from sensors to the back end. You want to build with one of the big thing is low power. Okay, we don't want to have big structures built in on the sensor chip because they consume more power and more volume or more water. Unfortunately, when you do, what are the things that you are sacrificing? Okay, functionally, you will say that, okay, I have the data, I have signal, and I have I made this processing, etc., and send the data very, very high speed. But probably when you scaling down the structure, scaling down the architecture, what you're actually taking away or making certain sacrifice are the issues like what you said, security. Okay, so but some applications which are especially like strategic applications and so on, for the ordinary, I would say, systems, their security may not be at a big stake, but for some systems where security required, invariably it has to be kind of a distributed, because each sensor is a weak node in your big system. If I have 1,000 sensor network, and if one sensor is the weak, that is my into a hole through which people enter in. So you cannot compromise in those occasions. So the security has to be also distributed, and they also have to be hierarchical. In the sense, I should have basic security that is built in the sensor, but at the same time, when it comes to my backend node, I should also have the further levels of security to ensure that no possible intrusion will take place. So there, you cannot play with the optimization of power and size, etc. alone, but you must also build an architecture which comes along with the encoding techniques, encryption techniques, which require additional space and power. So they must be also considered, especially strategic applications. This becomes very important. Yeah. I want to add into something about the Dr. Satyanarayana sir. I've been connected to Dr. Satyanarayana sir from last 6 years, and he's so humble, and basically he's a pool of knowledge. Whatever question you have, he is there to give a solution. And sir, I'm really blessed. 2 hours I was stick to the screen, and I was continuously listening to you. And truly, I request all the teachers who are available and listening to this workshop right now, if you have any such doubt on Industry 4.0, Dr. Satyanarayana sir is very reachable. You just ask him any question. He will be there to answer you. He is available in all possible social media. So you can always ask him any question, and he is very humble. He always answers a small question. If you ask, he is going to answer you for sure. So sir, thank you very much for accepting our invitation on the behalf of Electronics and Telecommunication Department and our management, principal and vice principal. I would like to thank you for sparing this time with us and imparting a knowledge on us on Industry 4.0. You have actually given all the possible Industry 4.0 applications to us today. Over to you, Ankush sir. Thank you, sir.
Thank you, Piyush. It's always a pleasure.
Good afternoon, everyone. On behalf of the Institute, the Department of Electronics and Telecommunication, Principal Sir, Vice Principal Sir, and everyone, we will like to express our sincere thanks and gratitude for enlightening us on various topics that we have covered today, like IoT system, VLSI, FPGA, cyber security analytics, plant phenotypes, sensor technology, chip technology. So a huge pool of knowledge is being shared in a very short span, and it was very well conducted, and everyone enjoyed it. And the session was very interactive, and everyone were able to interpret the information which was shared. So very thankful we are, and we are actually grateful that we were actually able to attend a session from you, sir. So very thank you, sir. And now I request all the participants to join the WhatsApp group. Those who have not joined the WhatsApp group, for the feedback and the quiz that will be conducted from 1 o'clock. So once again, I thank sir for an excellent session on behalf of the Institute Department of Electronics and Telecommunication, MCT Rajiv Gandhi. Thank you, sir.
Thank you. Thank you very much, Ankur. It is always a pleasure to communicate with such a nice audience. And also, I hope it was at the end something useful. And of course, we are missing really meeting in person and interacting, but I think this is the next best way to do. And let us hope that we soon will try to again reach and come to your campus. Thank you very much. Thanks, all of you, and also all the participants. All the best for the rest of your event. Thank you.
Sanjay Deshmukh, sir.
Thank you, sir. So we have a break now, and at 1 o'clock, we will be conducting a quiz relative to the topics today. And I request all the participants and the members, those who have joined, can give their feedback and give the quiz, attempt the quiz, and it will be conducted from 1 o'clock. So thank you very much. Over to you, sir.
Right. With the permission of Dr. Satyanarayana, sir, and with the permission of Dr. Sanjay Deshmukh, sir, can I end up the meeting, sir?
Yes, sir. Thanks a lot, sir. Thank you very much for your time and your valuable insights on Industry 4.0.
Yeah, thank you. Thank you, Dr. Sanjay.
Thank you, sir. I'll end up the meeting. Thank you very much.
Okay.